says one suggestion for powering spacecraft engines of the future is an ion engine. A beam of ions, charged atoms, is fired backwards, propelling the spacecraft forwards. In one test, xenon ions were used. A, consider how using xenon ions would compare with using krypton ions, which are lighter. If equal numbers of each were propelled back per second at the same speed, which type of ion would you expect to give more thrust? Explain your answer. So again, we want to answer this using the idea of impulse. The impulse given to the atoms is the force acting on them multiplied by the time it's acting for, but it's also equal to their change in momentum, which is their mass times their change in velocity. So the xenon ions have a higher mass and therefore a greater momentum than the krypton ions when traveling at the same speed, which of course it says they are here. It says traveling at the same speed. So we can say therefore that the force on xenon is greater. And so since the force on the xenon is greater, then because of Newton's third law, the force on the a spacecraft must also be greater. So the force on xenon is greater. So thrust on spacecraft is also greater when using xenon, or smaller when using krypton. Part B, let's get rid of that G so I can see the question. The mass of a xenon ion is 2.2 times 10 to the minus 25 kilograms, and it can be ejected at a speed of 3.1 times 10 to the 4 meters per second. Calculate the number of ions that would have to be emitted per second to generate a thrust of 0.1 newtons, a typical value for the thrust from such an engine. So again, we're going to do the force times the time is equal to the mass times the change in velocity, except now we know that it's not just one thing changing velocity. We want to find the number of atoms changing velocity. So I'm going to add in this second half of the equation a capital N, which represents the number of atoms that are changing velocity. So I want to find N, so I'm going to rearrange this to N is equal to the force times the time divided by the mass times the change in velocity. So the force is 0.1 newtons. The time, it tells us, is 1 second. We're looking at the number emitted per second. The mass is 2.2 times 10 to the minus 25, and their change in speed is 3.1 times 10 to the 4, giving us the number as 0.1 divided by 2.2 times 10 to the minus 25 multiplied by 3.1 times 10 to the 4, which is 1.5 times 10 to the 19. And then it's the number of ions. So this doesn't really have a unit, it's just a number, but we might write ions next to it to show that we know it's the number of ions.